Right, so we're going to talk now about the next section, which is all about variable acceleration. So you may remember from year one, we talked about displacement, velocity, and acceleration have this relationship, where if you differentiate the time, you can move sort of down, and if you integrate, you can go the other way. So what we're really doing then in this section is we're talking about variable acceleration, because when we have variable acceleration, SUVAT is another way of saying constant acceleration. That's not suitable anymore. The first thing we looked at in this chapter was this one here. This is about constant speed, so that's also not suitable. And we need to know when we've got the different types of acceleration. So here it says a particle's moving with acceleration given by this. And do you see acceleration has got t in it, so it means as the time changes, the acceleration changes. Now, we need to use then this idea of sort of differentiating down and integrating up. So the first thing we're going to do in this question is we're going to integrate it. Okay, and I've done the first bit already just to kind of get started. So I've said that if we integrate acceleration, we get velocity. And when we integrate cos, it's going to go to sine, isn't it? But also consider that 2 pi is a number, so we're going to have to deal with this as well. So this is our integration. We're going to get 1 over 2 pi because the chain rule, if you try and go backwards, that 2 pi will create a 2 pi, and we don't want it because there's nothing at the front here. So if you test that one there, that will work, and we've got the plus c. And with the plus c, we're often going to be using this kind of information to help us find it out. So we plug this in. When we do that, we're going to get the following result. So this is the v value for when t equals 0. And because sine of 0 is 0, it means that c is in fact this number. And it often goes that way. So what I've done now is I've written my final answer to the velocity to start with. So I've done the first part there. We're going to answer the rest of it now. So it wants to know the maximum speed. Well, there's no I in j just yet, so we're only dealing in one dimension. So the maximum speed is going to really mean the maximum velocity, and we've already got that. So what we want to do here is we want to think about a sine graph. So we know that a sine graph has a range usually between 1 and minus 1. So that bit there will always be sort of between 1 and minus 1. So when do you get the maximum? Well, the maximum, because you've got this positive bit here as well, it will happen when we pick 1. Because you'll get 1 over 2 pi times 1. The sine graph will give you 1. So having a good knowledge of the range of trig graphs is really, really helpful for this kind of thing. Okay, so I don't need to plug it into a calculator or something. I already know this, that it goes between minus 1 and 1. So when this is 1, you'll get that, plus the c bit, which we don't really have much control over. Okay, and then that gives you this as your final answer. So 1 over pi, and I'll just double check, but I think that's going to be in meters per second, isn't it? So meters, yeah, because that was it. That was acceleration before, which is meters per second. Lovely. Let's see the next bit. The distance traveled in the first 3 seconds. So a couple things in this one. First of all, distance. Distance, which one's closest? Well, displacement is sort of close to it, isn't it? So that's going to mean that we're going to want to integrate again from here to here. And then in the first 3 seconds means that it would probably be a good idea to do that. Okay, so to do some definite integration. So let's do those two things now. So first thing we're going to do is we're going to integrate this one here. So we're going to integrate, and rather than write it like that, if I factorize this bit out, it's a bit nicer. So let's instead take that out, because you can take numbers out to the front. So let's instead write it like that. Okay, and just test that it works, and it does, it takes you back. So if we integrate that with respect to time, we'll leave that bit alone. We'll do 3 and 0, we said. We'll leave that bit alone. Sine's going to go to minus cos of the same thing. And we also had that dynamic that we needed to sort of counteract against it, right? Otherwise, it creates a chain rule. So let's do something like that. 1 is going to go to t, because that's the thing we're integrating with respect to. All right, and then we would do 3 and 0 there. So what else are we going to do for this one? So it's going to be a case of evaluating it. So on a show that question, on a show that question, you might sometimes have to show some evidence of evaluating these things here. But because I don't want to make this video incredibly long, I'll just I'll just show you the first bit of what I would write down if it were me. So what's that? 3, so that's cos of 6 pi plus 3, minus, I think you get the idea. Okay, eventually that will give you an answer of 0.477 meters. So variable acceleration, we need to use the skills of differentiation and integration, and we need to scan the questions carefully to find the signals of which equation to deal with, because look, we've got acceleration, we've got velocity, and we've got displacement sort of being used here. There's quite a lot going on, and sometimes things, especially like B, can be even more difficult. Let's try another question. A particle of mass 6 kilograms is moving on the positive x-axis. The displacement is this. Okay, so we're sort of at the top of the pyramid, so we might have to do some stuff with this, or we might have to differentiate down. It's probably the way that it's going to go. Let's keep an eye on that as well. Velocity. Okay, so if I differentiate this displacement with respect to time, that will be the velocity. So what I want to do is differentiate this and then differentiate this in turn. So first one's going to be what? It's going to be 3 over 2 times 2t, and the new power would be a half. That's, I'm going to just rewrite that over here. That's a third e to the minus 2t, isn't it? So what's that going to become? That's going to become minus 2/3, and then the power stays the same with e. Okay, great. And then that's generally my velocity. And I want it at t equals 1.5. Okay, so we sub that in. So I suppose you can simplify that if you wanted to. 1.5 to the half minus 2/3 e minus 2 lots of 1.5 as well, and that gives you 3.64 meters per second. Okay. Given that the particle is acted on a single force, right? So they've talked about forces and they've got masses up here. So we might want to remember this one here. This might come in handy. So a single force, magnitude F, which acts in a direction with the positive x-axis. Okay, I think that's all fine. Find the value of F when t equals 2. Okay, so I think we want, well, they want this one here. We know this, and we kind of have a way of getting this. So let's write down an expression for the acceleration first. I think that would be a good idea. So acceleration will be the velocity now differentiated with respect to time. And where am I looking? I am looking up here. This is the one I want to differentiate. So this is going to be, there we are. So 4/3 t to the minus a half now. And then this one is going to get another minus 2, so plus 4/3. So they're both 4/3, is that right? Hang on a moment. There's a mistake on this one here, isn't there? 3 to the, right, let's just clean that one up. So I'm looking at my notes at the same time as well. Let's just write that one out a second. So what is that? That's 3t to the half. So that will be 3 over 2 now, won't it? So 3 over 2, t to the minus a half plus 4/3, and then this was e to the minus 2t. So that's the acceleration. And although things are changing, I've been given a particular moment in time. So when I find t equals 2, I find the acceleration at t equals 2, so I can find the force related to that time as well. So I can still use F equals ma, yeah? So at t equals 2, it's going to be 3 over 2 2 to the minus a half plus 4/3 e minus 2 to the 2, and this should give you just a little bit over 1.0850 ... is what I've got written down. And we're now ready then to write out f equals ma and hopefully make some progress with that. So f equals ma. I'm just writing capital letters. I'm not fussed about the vectors and all that sort of stuff here. It's all one dimension. So the mass was 6, wasn't it? So I think it's just 6 times that one there, which is 6.51 newtons is what I've got written down. Okay, so on this one, because we were given displacement, we were differentiating for both of them. So when you're at the top of the pyramid, you tend to go down. When you're at the bottom, you integrate up. Sometimes they give you velocity as a starting point because that's a bit more interesting. Differentiating down, generally much nicer. Integrating up, a little bit harder because you've got to remember about this plus c thing. And when we go on to 8d and 8e, there's actually 2 parts to the plus c. There's the part for the I and part for the j. But you should find 8c to be a fairly nice exercise in the book.